Sure. Okay. Welcome everyone in this live session of John Conway Spirited Seminar Series. Today we have with us Dr. Stefeno Luzzatto. To be very honest, he does not require any introduction, at least in the sense in Pakistani mathematical community. He's a quite a regular visitor, and he's currently affiliated with ICTP. And under his role in ICTP, he happened to be very actively working in developing mathematics in the developing world and connecting young mathematicians with the mathematicians from the European mathematical community and creating a lot of opportunity for the young mathematicians in almost all developing countries, including Pakistan. So currently he is our colleague. He is among the teaching team of the IIMM. So he has been teaching a course, and today we have a very special lecture by Stefeno Luzzatto, which I think covers a larger spectrum of sciences. Many people are interested to see the spaces with fractional dimension, which we call the fractals, and this is of interest of many.
Okay, well, good afternoon, everybody. Thank you very much for coming. It's a great pleasure for me to be here. As Dr. Imran said, I've been now coming to Pakistan for several years, working together with different people, and now with the colleagues at London International Mathematics Master, which has just started here. This semester, there will be several other international visitors will be coming. I hope that others will also give these talks, and they will benefit, all of you, the students and the faculty at London and other universities. So, yeah, maybe this one should be off, actually. I don't know if you can see. Yes, I think that's okay. You don't have to do that. So I'm teaching a course in dynamical systems together with Dr. Adnan. But I want to talk about a slightly different topic, which is also comes up in dynamical systems, but it's also much more general. And this is the topic of fractal geometry. And let me say that this talk has two purposes. One is that I would like to introduce this concept of fractal geometry, but there's also kind of underlying and more philosophical subtext. Maybe I need to advance. Yes. Yeah. Can you read? It's a bit small. Underlying meta text of the talk is the well-known question of what is mathematics. I'd like to, and I don't want to be too ambitious. What is mathematics? I think most of you will have asked yourself that question sometime. And one of the thoughts that is often expressed when thinking about this is, how come mathematics, that is such an abstract theory and it's developed so abstractly and conceptually, fits the real world? Or how come the real world fits mathematics? Right? And it seems almost like a miracle. So I would like to propose that there's two kind of views. So is mathematics a set of logically interconnected statements which by coincidence happen to describe the world very well? This is sometimes what it seems like is happening, right? Or is mathematics a language which develops out of human activity in order to describe it? It's not a coincidence that it describes the world. It is developed with the purpose of describing the world. right? So I don't want to spend too much time on this. And of course, it takes a little while to think really about this difference. But when we talk about a language, this sometimes seems like it is diminishing the importance of mathematics, but languages embody concepts and ideas, right? I think probably all of you here speak at least 2 languages, if not 3, if not 4. And you all know that sometimes there's some concepts, some things that you can say in one language that you cannot say in the other language. Okay? So that means that languages contain some concepts, right? And other languages contain sometimes different concepts. Do not always contain completely. And the language develops in order to describe concepts which are relevant to the culture, to the people. Right? So it's not a coincidence that our language describes what we want to describe, right? We're not surprised if we can say this is a table and it describes a table, this language, okay? Because the language was developed to do it. And mathematics, I claim, is like this. And I hope that in this presentation, I will somehow show you an example of exactly that. Okay, I want to.
Why can't it be a little of both? Why does it have to be one over the other? Like,
This
instances where one is a better description and other examples, but the other one is a better.
Perhaps. There's certainly the discussion of this does not finish here. There's a very sophisticated discussion, but I want to emphasize this part because that is the part that is usually missed sometimes. You know, people often
So why the mathematicians?
maybe maybe you're right. Maybe scientists and physicists don't take that point of view. Point taken. But I hope that in this talk, I would like to lead you to a journey, and I hope that by the end of the talk, you will have seen this in action, right? You will have seen how we develop a language that embodies a new idea that you did not have now. In 1 hour, you will have an idea that you did not have, and the language to describe it. So our setting is geometry. Geometry is the study of shapes in some sense. So what is it that comes to mind when I use the word geometry? What do you think about when you think of geometry? You probably think of this. This is what geometrical shapes that you're familiar with when you study school, right? What is the geometry of things that are out there? Usually looks more something like this. It's not that easy. Of course, you can try to patch together various of these geometrical shapes to try to describe these, but it's not so easy. Okay, so the question is this really, are these shapes that you find in nature some kind of composition of this, or is it a different kind of shape altogether that is more difficult to describe? So in the late 1970s, 1980s, a French-American mathematician called Abdus, he wrote a book that became very famous called The Fractal Geometry of Nature. And one of the quotes from this book, I claim that many patterns of nature are so irregular and fragmented that compared with standard geometry, nature exhibits not simply a higher degree, but an altogether different level of complexity. So this is what he's saying, that basically many of the shapes of nature cannot be reduced to a combination of these pyramids and spheres and so on. And it's somehow require a different language to describe this. And one of the fundamental concepts that we need to understand this is the concept of dimension. This is what we're going to focus on today. Concept of dimension. So the first thing I'm going to do now is ask you what you think is dimension. So we all can agree, I think, that line segment has dimension 1, square has dimension 2, and a solid like a cube has dimension 3. But if I ask you to define the dimension, how would you do it? How would you tell me what is the difference that really allows me to follow this dimension? Anybody have any idea? How would we, what is the characteristic do they have that's different? Parameters to how they get the space. The number of parameters to describe the space. Yes, anyone else agree with that?
Degree of freedom, the same.
Yes, more or less the same. Okay, so that is usually what is the main concept of dimension, right? So in the sense that if you have a line, you fix an origin, and then to specify a point in that line, you just need one number, right? Positive or negative number, like a real line, and that identifies the position. If you have a two-dimensional shape, you need two coordinates, right? You need to specify, say, the x and the y coordinate, and that specifies a point. So you need two variables to define one point. And here you need three, x, y, and z, right? So this is the most naturally, the way we usually think dimensions and the way we think. This is a good way in the sense that it's very easy to generalize to higher dimensions. Even though higher dimensions are not, our world is three-dimensional, so it's difficult to visualize something in 4 dimensions or 5 dimensions. But from a mathematical point of view, we just take 5 numbers and we kind of define them to define the coordinates of a point in a 5-dimensional space, right? So it's quite easy to generalize this definition. What about non-integer dimension? What about if I tell you that some object has dimension 2.5 or 1.5? Can we give some meaning to this? So with this definition, it's very difficult to generalize this concept because you can't say, well, I need 2.5 parameters, like x, y, and half of z. That is, you cannot. But very intrinsically in the way we define dimensions, by saying that is the number of parameters, it makes no sense to talk about something that has dimension 1.5 or 2.5, and therefore you could say there's no such thing, it doesn't exist. But what I want to convince you today is that there's something that makes very much sense, and I want to show you. We'll construct together some shapes and justify how the dimension of these shapes is somewhere in between these non-integer shapes. Okay? So to do that, interestingly, this is the first example in often how mathematics works, is we need to change our definition of dimension for the usual dimensions, right? So we need to find a way to define dimensions which somehow allows us to define something that's non-integer. So we're going to work with that. And to do this, we're going to do a little, okay, so first let me say that there's different ways to generalize this concept, which is what we're going to do. And just to point out, there's something called self-similarity dimension, which is what we're going to describe, which is easier to describe, but there is also a more general notion of dimensions of Hausdorff dimension. Okay? But we're going to talk about self-similarity dimension. This is what I'm going to introduce. Hausdorff is a generalization of this. And so the first thing we're going to do is we're going to look at our 3 standard objects. Okay? A line, unit segment, a unit square, and a unit cube. And we're going to stretch these objects by a certain factor in the following sense. Suppose I take the unit segment and I stretch it by a factor of 2. Then it's very easy. I just get 2 unit segments. I just stretch it by a factor of 2. And this unit segment is composed by 2 parts of the original. I would go 2, 1 unit, 2 of them, and 2. This seems obvious. But if we do the same thing with the square, what do we do? What happens with the square? So we stretch the square by a factor 2 in every direction, every point is twice as far than it was before. And we need 4 copies of the original square to make up something that is twice as. And with a cube, we are stretching it twice by a factor 2. And the stretch contains how many original cubes?
8.
8. 8 copies of the original. So notice already that there's something curious, that somehow is related to the dimension, right? And notice also that 2, 4, and 8 are powers of 2, right? So 2 is 2 to the 1, 4 is 2 squared, 8 is 2 cubed. And we use the word cubed actually for power 3. And this is related to this cube. Okay, so look at these numbers here, 1, 2, and 3. They somehow seem to be connected to the dimension. Okay, right? So let's try the same exercise, stretching by a factor 3. What's going to happen here? So we stretch it by a factor 3. We have 3 copies of the original. What happens if we take the cube and stretch it? We expand it by a factor 3. We will have 9 copies of the original. What about the cube?
What do you say?
Yeah. This is 3 times as big. I don't need to count this. So 9, 9, 9, and this is 27. So again, 3, 9, 27 are powers of 3. 3, 9 is the squared, is the cube. So this number 3 seems to be related to the stretching factor. And the power 1, 2, and 3 seems to be related to the exponent. Okay, so there seems to be, curiously, you can tell what the dimension of the object is by looking at these quantities. You stretch it by a factor, and then you count how many copies it contains, right? So summarizing this formula, if we have something of dimension d, for example, dimension 1, 2, or 3, and we scale it by a factor k, right? How many copies of the original does it contain? It contains n k to the power d. Remember, that's exactly what we had. So just to review the example we had, if the dimension is 2, for example, square, and the scaling factor is 2, right? You plug it into here, and we get 2 to the power 2, and we get n equals 4. That was the number of copies in the sketch, right? If the dimension is 2 of a square, and you stretch it by a factor 3, then we had n equals 9, which is 3 squared. 3 squared, right? Please interrupt me if you have any questions, okay, at any moment. And the same for the dimension 3, right? When you scale by power 2, you get 2 to the cube, which is 8. And if the dimension is 3, you stretch by factor 3, we get 26. All right? This is just to summarize what we have seen for dimensions 1, 2, and 3. So notice that this equality here is a relation between these 3 objects, n, k, and d. Right? And as all of you know, when you have this relation that relates 3 quantities, you can solve for any one of the 3 quantities, right? So you can write it. In this case, I've written it as n equals k to the d, because in the examples I was looking for, I kind of know the dimension. I know the, if I know the dimension and if I know the scaling, then I get the number of copies. Okay, but I can also solve this for d. Right? In other words, if I use this relation, I can use this relation to define d in this way. So those of you who know about logs, right? You take logs on both sides and you get log n equals d log k. So you get d equals log n over log k in these examples. So this is a suggestion that we could use these properties to compute the dimension, right? In the examples that where we had above, we were checking, we kind of knew the dimension, and we were looking at how many copies we had, and we were seeing what this relation was. And from this relation, we get this. And then we say, okay, we could now solve for it, and we can use this as the definition of dimension. And if we use this as a definition, it corresponds, right? In the cases when dimension is 1, 2, or 3, it gives us exactly the dimension 1, 2, or 3. Right? When we plug in n, we fix the scaling, we compute the number of copies, we compute this, and we get exactly. But already this is now a different formulation of dimension. It's not in terms of number of variables. It's something that, at least in principle, does not have to be an integer. And in fact, when you look at it like this, you're surprised that it's ever an integer. Right? You don't expect this to be an integer, but of course, in these particular cases, it turns out to be an integer. So we're going to use this formula. This is the most technical slide I have. I don't have a lot of formulas. And in this way, right? So what basically this formula says, okay, I take a shape, okay, and suppose I scale it by a factor k, and then I count how many copies it gets, and then I plug it into this formula, and I compute the dimension. Right? So this is what I'm going to try to do. And I'm going to do this for this example of this curve called the snowflake. And this curve, what's that? Oh. Okay, this is a geometric shape that actually was found by more than 100 years ago by a German mathematician, like Helge. And it looks like this. And of course, when you look at it like this, you have no idea what you're looking at. Maybe we're going to understand it a bit better. We're going to see the construction, and we're going to try to compute the dimension of this curve. This is a curve, closed curve. So to do this, I want us first to, yes, so as we shall see, it has infinite detail, is one of the interesting parts of this. Notice, first of all, that this curve is constructed on a triangle. So it was not completely obvious before, but actually it is a curve that basically has 3 sides, right? And it is a construction. The construction on this side is identical to that on this side and is identical to this. So all we need to do is show the construction on an interval, right? And then it will construct. It will be the same thing on all 3 sides. So how do we do this? So we start with one side of that triangle, straight line. It is an iterative procedure. So what's the first step of the iteration? It seems very simple, but don't blame. So the first step is to take this, let's suppose it has length 1. And then we divide this into 3/3. We remove the interval in the middle of length 1/3, and we replace it by this little tenth. So we replace it by 2 intervals of length 1/3. What is the total length of this? 4/3. And so we've increased the length. We've replaced these 3 intervals by 4 of exactly the same length. And the next step, we do exactly the same thing on each one of these. So we take this interval of length 1/3 here, and we chop this one into 3 equal sides, equal parts. Therefore, each one has length 1/9, right? And we replace this middle bit of length 1/9 with 2 pieces of length 1/9, which make a little tangents. And then we do exactly the same here. So this is also an interval of length 1/3. We chop it into 3 equal parts. We remove the middle one, and we replace it by this little tenth. That is 2. And the same one here. What's the length of this? Yes. 16. How many pieces do we have? 16. Right. So here we had 4 pieces. And then now we are dividing each one into three, and we're replacing this 1/3 by 2/3. So what was our length 1/3 is now becoming 4/3 multiplied by 4/3, right, of that length. So each time you're multiplying the length by 4/3, actually. This is just an observation that is not so crucial, but it's an interesting observation. Okay, so we have this, and then we're going to continue to do this. What's the third step? We do the same, right? So I'm not going to put it here, just put each segment the size 1/27, because we take this little one here, which is this, we cut it into 3 equal parts, and we put the little text. And we do it for each one of these 16 intervals. And now we get 16 times 4/3, whatever you can count them, you can take the length, so okay. And then we continue, right? So here we now have, they're getting very smaller, so it gets more difficult to do it each time. Unfortunately, we're not mathematicians and not physicists, so we can keep going as long as we want. And in the end, so this is a mathematical step here, a non-trivial mathematical step, which is that we take the limit of these shapes, right? So this is something that you can formalize mathematically. It's very similar to taking the limit of a sequence. We have a sequence of geometric objects, and it's possible to show that in some sense, as you continue this iteration, the shape of this object is getting closer and closer and closer to an object which is called the limiting shape. Okay, it's a bit more sophisticated version of a converging sequence. It's a converging sequence of shapes. Okay, so this shape that you get in the end, the limit as infinity, is not the shape that you can draw. In principle, at every finite stage, you can draw it, because at every finite stage, the shape is just a union of tiny little segments, right? Although it becomes millions and millions and billions of segments, so they're very small. But as you keep going, it's getting smaller, and so it's getting closer and closer to this shape. This shape, yes.
So, as we go from n to infinity, don't you think that the segments are getting smaller and smaller, and it appears as is a continuous line?
It is a continuous line. Well, continuous. So let me specify. So what is interesting?
Smooth, I think.
Yes, no,
becomes
it's
smoother.
the opposite. It's the opposite, right? Because it's very zaggedy.
Oh,
It's very zigzaggedy, right?
I was just
And this is no, but this is exactly very good observation. So I will not prove it here. It takes a little while to really understand. But this limiting shape does not contain any segments and does not contain any smooth curves, because everywhere there was a segment, at some point you put a bump, you put a zigzag in there. Right? This is a very interesting feature of this limiting curve. There's anything flat. Wherever you look, you know, you would hoping to find at the finite stage you've got a little flat segment, but sooner or later you're going to put a little zigzag in there, and then in each one of the slides you're going to put a little zigzag. So the limit is nowhere differentiable. In fact, the title of Koch's paper was a nowhere differentiable curve. It's nowhere, it's zigzag. That's what I meant by infinite detail. In that, if you take a segment and you zoom into a piece of the segment, you will just see another segment. You cannot tell where it are. Okay? In some sense, this is also similar, as we shall see, but you never get to anywhere flat. So let's study this shape in a little bit more detail. So what does this shape look like? Notice that, remember, let's look at this and remember a little bit how we started by the construction, right? Remember that this was a unit interval going from here to here. And then we cut it into, we took away the middle third, which is exactly this, right? And then the horizontal length of this is 1/3. The horizontal length of this is 1/3. This is 1/3. This is 1/3, right? Remember, that's how we started the construction, right? And then we started taking away 1/3 of this and replacing it by these 1/9, this was 1/9, and so on. So if you think about how we did the construction, notice that this little piece here, if you think about it, is exactly 1/3 copy of the whole picture. Because if you stretch this by 3, you see that the horizontal, this was 1/3, it will have length 1. Right? And if you look at this vertical height here, it is exactly 1/3 of the vertical height here, because it is the next step of the construction. Right? So if you take this and you just stretch it by 3, you will get that this horizontal base will cover everything. This vertical will be exactly this length. These sides here will map exactly to these sides here. And in fact, everything will match up exactly. Right? Which does not happen if you do it at a finite stage of the construction. If you do it at a finite stage of the construction, then here you have one step more or one step less. Sure, okay, but you do not have that these will match exactly. It's only this limited picture that will match exactly. So this piece of curve in the small rectangle is an exact copy of the whole thing, but 1/3 size. Okay? How many of these are there? You can see them. It's 1, 2. This one is the same. This one is also identical to this one. And this is exactly 1/3 of this. So now you need to stretch it. You also need to rotate it. Okay, but up to rotation, you will get exactly the same thing. So the length of this is 1/3. Maybe the picture is a little bit squashed, but so it doesn't look exactly like that. But if you think of the construction, this length is exactly 1/3. Everything is exactly the same size as this. This copy here, if you just take this copy and you put it on here, it will match exactly, right? So this is also 1/3 of the copy. This is also another identical copy. This is also another identical copy. So all these 4 copies, they're all identical to each other, and they're all exactly 1/3 size of the whole thing. So we have this whole shape is made up exactly as the union of 4 identical copies, each one scaled up. So remember formula. So you can already see that this does not match neither the 1 dimension nor the 2 dimension. When you scale by a factor of 3, if it's 1 dimension, it's made up of 3 copies. It's 2 dimensional, it's made up of 9 copies. This is made up of 4 copies. Oh, it was like 4 copies. Right? So if we use this formula for the dimension, we get log 4 over log 3, right? Because 3 is the scaling factor. 4 is the number of copies. Remember, we said we could use this as the definition, and we get something fractional between 1 and 2. 1 on 2 6. So if we use this as our definition of dimension, we've now constructed relatively easily a shape with dimension. It makes sense. It is consistent with our notion of dimension 1 and 2 to say that this is dimension 1. So let's see some other examples. Now that we know this construction, we can easily construct lots of other examples. I'm just going to show you. Okay, so the conclusion is that Cox snowflake has dimension 1. So we can easily construct other examples. Now, look at this example here. So here we start also with the unit unit interval. We also divide into 3 equal parts. We remove the middle one, but instead of putting a tent, we put a little house. So we now, instead of replacing it by 2 pieces, we replace it by 3 pieces. Right? So we now have 5. 1, 2, 3, 4, 5. This new segment, this new shape is composed by 5 segments. Each one is 1/3. of the previous one. Okay, exactly. Same, and you see we do the same thing here. So now we take each one of these, we take this one here, and we take the middle 1/9, and we replace it by the house. We do the same thing here, same thing here, same thing here, same thing here, and then we keep going, we go to the limit. Exactly in the same way as we do. And when you look at this, you will see when you look at this closely, and you remember that this was really built on this shape here. Like you see that this is 1, 2, 3, 4, 5. Each of these you have 5 pieces, because actually once you get to this stage, you're now doing the construction of each one completely independently. Right? So you're doing exactly the same construction on each side. Yes.
Can you go on the previous slide? Yes, in this figure, you say that this curve is in the construction triangle. So with the dimension, this will be if you think that this is actually the construction here.
Thank you, Amara. That's a very good question. So in the end, if you do, the dimension is determined by the construction that we do on each side, right? Because on each side we do the same thing. And so you can do the same calculation and you will get this curve here has this dimension, so does this, so does this, so the dimension, they don't add up. Like if you take 2 cubes, the union of these 2 cubes still has dimension 3, right? So it's the same thing here. So you can do the same construction on a square, and you do on each side of the square, you do this, and you will get a shape that looks like a square, and on each side of the square, you get this, so you get both sides, but that doesn't affect the dimension, right? Because on each side, you're splitting into 3, not into 4. So on each side, you're doing this construction. Whereas here, you are doing something different, right? Because you have chopped this into, you've replaced these 3 bits by 5. It's not by 4, right? So it's a different shape. And then you do the same thing. You go to the limit. You see here there is 5 pieces. So now it's still stretched by a factor 3, right? Because each one of these is 1/3 of the whole thing. So if you look at this piece here and you stretch it by a factor of 3, it will map to the whole thing, right? Because this will stretch the whole length, this will stretch this, so it's still stretched by a factor 3, but there's 5 copies that make up this. Okay, so what's the dimension going to be? Log 5, like log n over log k. And the k is the stretching, and so this gives something like that. You can also have very different shapes that have the same dimension. So this shape here is constructed in a slightly different way. You're not removing anything, but you still start with a unit interval. You divide it into 3/3, and then you just add these 2, right? And this still now gives you 5 pieces that are exactly the same. And then you repeat on each piece, you repeat exactly the same construction, and you will get exactly the same thing here. That this piece here, when you stretch it by a factor of 3, k is always the same, right? Because you're going to do a certain construction here. When you stretch by a factor 3, we get a copy of the original thing. So this will then map to this big thing. This here will map to this big thing. So you stretch, you can check. And so here you will also get log 5 over log 3, because the stretching factor is 3, and the number of copies is going to be 5. Also here. Right? So just like in dimension 2, you can have a square, you can have a kind of polygon, you can have very different geometrical shapes that have the same dimension. The dimension obviously does not characterize the shape. It measures something else, like the dimension in some way. Same thing here. Okay.
Okay, so my question is that if you have a real number, given a real number, can you construct a fractal?
Given a what?
Given a real number, any real number, can you construct a fractal that has exactly the same dimension?
I don't think I know the answer to that question. I presume yes. It might not be self-similar. As I said, we're using here this concept of self-similarity, right? We're using the fact that small copies are identical to the big one, and there might be some constraints because of that, but I don't know It's a very nice question. In general, for household dimension, you can define, as I said, I will not talk about it, but you can define a more general notion of dimension, which coincides with this dimension in these examples, but it does not need to be self-similar. You can have shapes that are complicated, and there certainly you can have any dimension.
Okay, so once you've constructed your curve, does it have a length that can be defined?
That's a very good question, and I was not really going to touch on it, but I think it's a very good question. So the measure of the size of a geometric object depends on the dimension. If you think about it, right? When you measure the length of a curve or the area of a square, you're using different measurements. You're using length in one case and area in another case. It's two different ways of measuring the size. If you try to use length, which is a one-dimensional measurement, to measure the size of a square, you will get that it is infinite size, right? Because if you use area to measure a curve, unless it's an extremely complicated curve, you will get measure zero, area zero for that curve, right? So this touches, in fact, this is what the generalization to household dimension is based exactly on that. So there is a way to generalize the notion of size, and there is, for every object, there is a cutoff size underneath on one side of which the size is infinite, on the other side, size is zero, and that cutoff is exactly the dimension, right? So if you try to measure something two-dimensional with a one-dimensional length, you will get infinite length. If you try to measure it with three-dimensional volume, it will have zero volume. You need to measure it with the right kind of measure, right? So there is measure that, given the dimension, a measure that will be finite or that will be appropriate to that particular dimension. In fact, this is essential for the definition of the non-general path. That's how the non-general path. Negative dimension, I don't know what that means. Yeah. Well, in this case, you cannot get it because you're looking at the number. If you scale by at least by something bigger than one, then you always need more copies. So
This will work even if you take numbers less than one. For instance, you take a line and you chop it into two pieces, you're still going to get two pieces for the same line. So the same definition will work even for numbers.
oh, sure, for integers you mean.
No, for numbers less than one. If you scale them, you're still going to get.
Yes, that's a really good question. To be honest, I never even thought about it. I don't know if anyone thought about it. I wouldn't know how to give a geometric interpretation of negative dimensions. I'm not sure, but you never know in mathematics what you can give meaning to. Yes.
We can also do that.
So, yes, of course, you can have zero dimension. If you take a point or a union of points, or they will have zero dimensions. If you have a Cantor set, it does not always have zero dimension. So you can have, so the usual Cantor set that is most familiar to most of you is the middle third Cantor set, is zero dimension. But you can also, no, it's not zero dimensional, sorry. It's not zero dimensional. The Cantor set is, can't remember, but you can, it's similar, so it's log, so then 2 over log 3, exactly. Log, yes. So it does not zero dimension. And you can, by changing the gaps in the Cantor set, you can get all kinds of dimensions. Probably by changing the gaps, you can get any dimension. Zero dimension.
Can we say something about the uniqueness? Maybe we look at in some cases, maybe we use the differential scaling and get different values for
So the geometry is very rigid. This D depends on the fact that we constructed exactly that way. Of course, if you start sketching things in different way, the dimension might be different. It depends exactly what you mean by that. But Yes, this dimension is something that depends very much on that particular size. Yes.
Okay, so here the respecting the measure.
Yes, this was something that this one was asking. So we can define some natural measures that measure the length, the size, in a way that is appropriate to that dimension. It's called the household measure, right? So the one-dimensional household measure is one-dimensional Lebesgue measure. The two-dimensional household measure is two-dimensional Lebesgue measure area. The three-dimensional household measure is just volume. Right? But volume, area, and length really are appropriate to measuring shapes that have that dimension. And the household measure is appropriate depending on the household measure of dimension 1.5 is appropriate for measuring the length. So this one has curiously exactly measure 1.5, right? Because this one, you see, you divide it not into three, but you divide it into 4 pieces, and then you put 1/4 here and you replace it by 8 pieces. So you will get kind of 8 pieces that stretch by a factor 4. And so this contains 8 identical copies. Each one is 1/4 of the original, and so you get the dimensions again. And you can define a measure. But that is quite sophisticated to define a measure. So you have to. So yeah, so this is really as far as I want to say really in terms of mathematics of it. I think it's very fascinating because, as I said, it's really, I hope I've shown how mathematicians create the language to describe new objects with new features, right? You create the language that describes new characteristics of the shape. And it's a very creative process in some sense. This shape in some sense exists and you're developing the language and the tools to describe it. So as I said at the beginning, Mandelbrot was looking, so these shapes were already known more than 100 years ago, right? The snowflake curve was at the beginning of the 1900s. But Mandelbrot was a kind of mathematical physicist, and he said, okay, I think this is the correct geometry to describe nature, really, not squares and triangles and so on. And in nature, we do also tend to see some level of self-similarity. Of course, not at too many scales. You cannot have perfectly similar shapes because objective reality has certain limits, cannot be too small, cannot be too big. But you do have, everyone is familiar, for example, if you have a tree open, a branch, if you remove a branch from a tree, sometimes it looks the same because it itself has smaller branches coming out of it, and sometimes it's not clear at which scale. If you just have a photo, you don't know if it's a tiny little branch or if it's the whole tree, right? They look alike, they're just scale. So you get a lot of these shapes in a very natural way. This is a kind of broccoli, as you know, you see it's got these shapes, and then on top of each one, it's got these little ones, and then these tiny little ones. So it's you see the shape repeating across this. This, to be honest, I'm not sure if it is kind of ice on a glass, or if it's maybe a satellite picture of something, right? So this is another interesting example, is that you cannot tell from this picture if it is something microscopic or if it is something, of the scale of a satellite, because these are shapes that you see in many different situations. So just what I said before is that you can also define lots of non-self-similar fractals. One easy way, so these are perfectly self-similar. You see the same shape at every scale, right? You see the small part that's identical, and so on. But of course, there's many ways in which you can do that. So for example, you can construct examples with different shapes at different scale. For example, suppose I construct a snowflake curve for 1,000 iterations. So I have tiny, tiny little lines. So it's converging to the snowflake curve. But then when I have, I don't know how many intervals I will have, then I change the construction and I do one of those other constructions, inside these tiny little intervals, I start putting the little house instead of the little tent, So in some sense, what you see from afar looks like the snowflake, but then when I zoom in fast enough, suddenly I see it's the different shape, it's the other factor, that different scale, right? So scale is one of the fundamental concepts, not only in mathematics, but in physics, especially in physics, right? Scale, what you see at different scales, is one of the most fundamental concepts. And this is one thing that we see very much in a mathematical model that some of you must be familiar with, called the Mandelbrot set, in honor of Benoit Mandelbrot, the mathematician that I said before. And I do not have time to explain this particular shape actually is very much related to dynamic systems, which is the field that I work in. And it is constructed algorithmically, iteratively through the dynamics. And this boundary, the actual Mandelbrot set is the boundary. So there is here a black shape, and there's an outside, and then there's a boundary, which is very, very irregular. And you can see lots of amazing pictures from this boundary. You can build on the computer. Some of you must have seen this, and they're really amazing. These are all shapes that are inside this Mandelbrot set, full of details, you see. And then sometimes when you go very deep, you see little copies, self-similar. There's a level of self-similarity, not exactly self-similarity, but you see some so-called baby Mandelbrots. And I just want to finish with a little video. You can find there's a little video. People make these videos in which you zoom into the Mandelbrot set and you see all these fractals, right? And maybe if we can look, so these are just other pictures. Okay, so this is the video. Let's see if it will play. Can I open this? Yeah. Just a few seconds of this. Oops. Find this YouTube. How do I go back to the Zoom or to the slides? Okay. Okay. Anyway, that was. That's. Thank you very much.
Are there any comments or?
I have
Yes,
one
sir.
more question.
Sure.
Can we talk about the dimension in the case of non-self-similar vectors or?
Yes, yes, there is this notion of half-of dimension, and it is based, as I said, on this way of measuring size of the set. So first you need, there is a general way of measuring the size that depends on the parameter S. And as this parameter S varies, you'll see that there's a threshold, right? Depending on the object that you've got. And below this threshold, the measure of your set is infinite. And that means that you're measuring with an S that's too small. It's like measuring the area of something with a one-dimensional measure. And above this threshold, the measure is infinite. It's like measuring the area with the volume measure. Sorry, above this is zero. Yes, above this is zero. And there is one cutoff point. And that is the house of dimension of the set, right? So exactly the value of S or D, that on the one side, the measure of that is always infinite, on the other side is always zero. If there, in that point, it could be zero, infinity, it could be finite. And that's how you define the house of dimension, basically.
And the house of dimension matches with the self-similar ones in case it has house of.
It matches with that, and it matches with the regular dimension in the case 1, 2, and 3.
And just out of curiosity, what is the dimension of letter process?
Okay, I didn't want to say because it's strange because the dimension is actually 2. It's 2, but it's still a curve, you know, it's not, it doesn't have any interior, it doesn't have any ball, it does not contain any ball. So it's so wiggly that the dimension is actually 2. This has been proved. This is a major result about 20 years ago, a very highly non-trivial result, that the dimension of the boundary of the boundary of the set is 2. Slide of the snowflake. So I cannot hear you. Yes? Yes. I don't understand your question. So the dimension is not something that we decide, right? The construction gives a shape such that if you look on one side here, you see that this full shape is made by the union of 4 identical columns. Yes.
So that there are one portion is fixed.
Yes.
So how did you get the dimension of four?
Right, it's the same, right? It's the same as if you take these squares, the dimension of the union of the squares is 2. It does not sum, right? The dimension is not sum, but the dimension is a measure somehow of the thickness of the geometric object you want, right? So if you take one segment, or you take 2 segments or 3 segments, dimension is always 1. So the fact that this is formed by the union of these does not affect the dimensions, because they all the thickness of this boundary.
So, Stefano, whether this particular procedure is generalized for instance, you started with a particular sphere shape and then you keep on doing so. Fractals, just like when we are going on the curve. So what about starting with a 2-planar object and doing the similar iterative steps on a 2-dimensional object? Then definitely this is going to be something surfaces.
Yes, you can do that. There exist examples. For example, for instance, there's a classical example called the Sierpinski sponge, right? Where you take a cube and you remove bits in this way, right? And you end up with an object that has dimension less than 3, because you remove so much stuff, and it's self-similar, but it has dimension less. So you can do it, but it's more difficult because in higher dimensions.
But in that particular case, the same formula works, I think.
Yes, because it's self-similar, because if you take, I cannot remember exactly how you compute it, but I
same
think
one.
so, I think so.
What do you mean by the problem? What's the problem?
For instance, if you start with, for instance, in the Spinsky's triangle, you should start with
Or in the triangle,
tetrahedron.
you take the solid, well, you can do it either, you take a cube, solid, and you start removing.
I get that, but you're saying the same problem occurs. What is the problem? that you're
The same
referring to?
formula.
Same formula.
Oh, the same formula.
Yeah.
Oh, right, sorry, I missed
The
that.
same formula.
Right.
Yes.
Would you please go over the video set because it has to do with other one.
Yes.
It also doesn't read this.
So, after my thanks, there are some hidden slides here, which go through this, but I don't think we have time unless maybe if anyone is really interested, you can stay, and I would be very glad to go through this, but it's true. So these Julia sets come from these iteration dynamical systems on the complex plane, and that's what defines the Mandelbrot set. But I think that is now only for people who really are interested in that. Yes. Sorry,
Going back to the smooth plate, so you said that it's not differentiable, of course, but it is still continuous.
Yes.
Is the topology of that curve still certain?
You mean if it's homomorphic to a circle? I believe so, yes.
Even with that cube, if you are using those things on the inside of the wires.
No, when you remove it, you get something like when you create a Cantor set, change, you get something that is not homomorphic when you remove stuff. But in this case, you get something, homomorphisms can be very wild, right? Continuous maps can distort very much. So that's what I see. Okay, so this is the household measure, just for you. If you wanted to, that was the measure that I was talking about, but we don't need to go into it, but there's a formula for the S-dimensional measure, and then there is a cutoff point between which is infinite and 0, and then we have the so it's actually simple. No, that's a good question. I have heard about it, but I don't know anything about it. Yes. That's a good question. I don't know about that.
I know somebody who worked in fractional differential equations. I
Yes.
asked him to explain the idea to me once. He took it upon himself to try to explain it.
It's not clear that there is a
Might be related.
Yes. Yes, it's a good question, and I don't know the answer.
Can we get the preference to the semester? Let me
I don't know exactly what you mean. I mean, these are geometric objects. It's a shape in space, right? Because what you're talking about is process. So I'm not sure. I mean, they arise. Objects with fractional dimension are very natural. The usual geometric shapes have been known for 2,000-3,000 years, and that's what we teach in school. We should be teaching fractals already in primary school actually today, because they are just as natural or even more natural, right? And it's not actually that difficult. I mean, there is something like this limiting process, of course, to formalize that is a little bit tricky, but the general idea and the pictures are quite fun. And so they are, they're geometric objects. And so they arise very naturally in lots of domains. So that's what I was getting at. So they arise very naturally in dynamical systems. Perhaps they arise in stochastic processes. I'm not an expert.
not be achieved because a specific part of that sector to contain the dimension.
Yes.
So if I take some other part, then dimension will change.
Yes. No, the particular case of the snowflake, the dimension is the same
Now,
everywhere.
so there it goes. But if I take some other part
Of that particular snowflake, you will always get the same thing. And that, but because that is up. Yes. Yes.
if I take some other like that is different from that.
Whose geometry is different? I mean, if I take a piece of this particular shape,
Like the one that
if I just take this bit here, this one, no, I will get exactly the same thing because you see, this part here is formed by two pieces that are identical to each other and identical to this whole piece. And I just will not even be able to tell the difference, you know? If I just take this piece here and I calculate the dimension, I will get exactly the same value. In this particular shape, any little piece I take will, when you scale it enough, will give you the whole thing. So it will always be exactly the same.
But this would be true for all subsets.
Sorry?
This thing would be.
If it's
true for all-
completely self-similar,
For all,
yes,
for all subsets.
because it's by definition constructed to completely self-similar problem. As I said, you can also try to put people and after a certain level, you change the construction. So when you're at that scale, you see something different, and then you will get what you're talking about, right? So you go to a very small scale, and suddenly you see, so if that little piece has a different consequence, that is different to self-similarity.
and then I split into the triangle and the shape of triangle and the and we find the dimension. How about dimension?
That is a very good question. I think probably you will not be able to define the self-similarity dimension in that case because we are fooling the system. And we are switching each time,
Yeah.
and so you will not get something that's self-similar. So that's very clever. You can still use a household dimension, that's all.
Stefano, one last question. Did people try to do the same thing by maintaining the continuity of the differential building in the sense, for instance, dividing the line into the three parts, but in the middle part, instead of putting the triangle, why not a semicircle kind of thing? And
That's what I
keep on doing. So I don't know.
I don't think you will be able, if you try to preserve smoothness, you will not be able to get something back. You will not be able to go to the limits.
But
My-
for instance,
my
if
smoothness.
someone tried to do it with circles, the fractals would be
I think,
probably.
I don't know, we'd have to see in a case by case, but I think once you go to the limit, if you have anything smooth, you will have dimension one.
Yeah, I
In the
completely
limit,
agree.
right? So in the limit, if the limit has a piece of straight line or smooth curve, it will have dimension one, at least that piece. And,
So- Yeah.
yeah.
Okay, are there any questions? I think the questions, the comments can continue over the tea. So it's time.
I would step two though.
Yeah, the same 1/3, dividing the other segment into one and the small segment. Yeah.
So how do you divide the circle?
Yeah. Then
Okay, we can.
one has to sit. Yeah, that's the thing. Yeah. Yeah.
Thank you very
Anyway,
much.
yeah.
Sorry, oh, there's a question.
No.
There's a question in the chat. Just came in.
I don't care.
A general question, where do we usually see answer of dimension? We use in pure mathematics. Measure is measurable.
Yes. Sorry, I don't know if the hearing name.
We'll stop. You can just answer it. Over here.
Hello, yes, sorry, I don't know if you can hear me, but the house of dimension, house of measures are used ubiquitously in lots of areas. of mathematics wherever objects of fractional dimension appear. So it's actually a very important fundamental object like measure theory. Any course in measure theory will contain household measure and therefore household dimension.
All right, thank you very much. So we'll
Thank
close
you.
this recording now.